So this is going to be our demo for code segment 1. So in code segment 1, here we have our code, and this code is the altered code to have nested loops. So unlike the original, it has call functions within other subroutines. So I will step through it with debugging and show you how each one of those works, especially taking care to look at the stack and the program counter. So the program will start by jumping to main, and then in main it only has one call, and it's to the first subroutine that has all the other subroutines nested within it. So this is our initialization subroutine, and right here you can see that the program counter is at 100, which is in hex, but just to make it easy, it's at 100, and the stack pointer is at 8FF. So if I go into this call, it'll hit this label and go to this line. So now we can see that the program counter has skipped to 104, and instead of just going to the next line, the call lets it change the program counter to whatever label you're trying to go to. So you can also see that the stack pointer is now at 8FD, and this is because the return address for when the ret call is hit is now stored onto the stack. So if you look at the bottom right of the screen, you'll see that in the data mapped IO memory, you'll see the two new red values. So that's going to be the memory address 102, and that's the return address that the program will be returning to once that red call is hit. So this is the initialization subroutine, and it basically puts the count in a register and then sets the quotient and the remainder to the count. And then, instead of going back to main, now we call the getNum subroutine. So now, with the program counter at 10A, it's going to jump directly to 10D. And our stack pointer has now also gone back and is at 8FB. So now you can see that another value has been added to the stack, and that is the return address for that second subroutine. So now we are in the getNum subroutine, and this is just going to put our dividend and divisor into registers, and then we're going to hit our third subroutine, which is our testing subroutine that tests these dividend and divisors. And once again, the program counter and stack pointer are both going to change. So another return address has been added to our stack. And now we test the dividend and divisor values just to make sure that they are valid to use for this division. So you check if the dividend is 0, you check if the divisor is 0, you check if they're equal to each other, and then you check if the dividend is less than the divisor, and if any of these are true, then the program would halt and would not continue. So since we have passed all these tests, we're now going to go into the divide subroutine. So we can see once again that our program counter and our stack pointer has changed, with our final memory address being put onto our stack. So when the two values are actually divided, we're going to subtract the divisor starting from the dividend. So we're going to subtract the values of R31 from R30, and that's going to keep going until our 30 hits a negative value. So once it has hit this negative value, then this compare will actually no longer branch, and we're going to decrement the count by 1 and add the divisor back to the result, and then store the count as our quotient and store our remainder. And then we finally hit our first ret command, and with this command we'll see that the program counter and the stack pointer both change. So the program counter is going to get changed to whatever is currently stored on the stack, which is our return address. So we should see it go back to 130, and here you can see the program counter change back to 130, and the stack pointer moved up because we no longer need that return address. And the same thing's going to happen for these next few ret calls. So it's just going to keep moving up, back up in the program, and the stack is just going to keep moving up because we no longer need those values until we finally get back to our original stack pointer value, and we are now at the loop that halts the program.
So code segment 2 begins by loading the ZL register with the low function of 2 times table, and 2 times table gives the value of the location in the flash that is equivalent to where this label is for this data table. And so then the high bit is also set to Z high, so the Z register just contains the address for the actual location of the table. And R16 is then, and that happens to be 598. And then R16 is loaded with the value of Celsius, and Celsius in this case is 9, and 9 is going to be the index of the byte in the table that we are looking for, because whenever we add that to ZL, that is going to increase the number of bytes and the address for that to make it so that the location of Z is now exactly at the value of the value in the table that we are looking for. So it contains the address of the value in the table that equates to the Celsius for 9 degrees. And that is why we add it here. And then we load R16 with 0 directly, just so that whenever we perform this add with carry, we're not actually adding anything unless there is a carry bit, in which case ZH will go up just so that Z remains consistent. And then LPM looks up the value in the flash memory where Z is for the address of Z, and stores it in register 0. And so it loads the actual byte that the address is referencing, which in this case is the Fahrenheit value of the index that we got for Celsius degrees of 9, which if we look down here should be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 48 degrees. And if we go to the next one and we STS, so we store that into the SRAM from R0, then we can see that in the SRAM here, we have 30, but 30 in hex is 48, and so that stores the correct value. And then now we get to the sorting, and so sorting is going to go through the toSort data table, and it will sort this random assortment of numbers from lowest to highest. And so in order to do that, it first stores the number of times to loop through the list. So we're going to be doing a bubble sort, which is why we have the n minus 1 for the number of times that we need to go through the table, where n is the number of values in the table. And so then we also do the same thing for the actual values themselves. And then we store 0 as the current value for both the number of loops we've gone through and the current number of values that we've gone through. And now we're going to set the X register to location 0x0100 in SRAM. And so, because the reason why we're doing that is so that we can store the values that are currently in Flash in the database eventually to SRAM for output. And we can also work with them easier that way because we can increment through the address that is in X. And so then we do the same thing that we did with the table that contained all of our Celsius to Fahrenheit conversion. And we're going to do that 2 times the label and set the low bit in the low bit of Z and the high bit in the high bit of Z. And then we get to store SRAM. And so what this is going to do is actually go through each individual value in the table and store it all in SRAM. And so if we look over here, we will see that we load the address stored in the Z registers, or we look up the value of the address stored in the Z registers and stored in R0 so that we can operate. And so R0 is here. And so our first one is going to be 27. If we look down here, our first thing in the table is 27. And then we are going to store that value in SRAM. And so 27 in hexadecimal is 1B. And so that gets stored successfully at 0100. And then we're going to increment R19. And so R19 is going to be our current value loop through. And we're going to use that so that we can go through every value in the table. And so we're going to repeat this multiple times. And if you look to the right, each one is being stored. And at the bottom in watch 1, we have R19 slowly going up, and eventually it will reach the 19, where we have currently, we're comparing R19 to R17, where R17 is our reference of 19 values that we have to go through. And the BRLT is branch if less than, so we go back if it's less than or equal to, which will give us all 20 values instead of just 19. And so we will continue to do that. And now that is the 20th value, so we branch if less than, that's not true, branch if equal to, that's also not true. And so now we get to list loop. And so list loop is going to loop through the list of values multiple times. And then every time that we do that, we need to reset R19, and we also need to reset the address of the current value that we're looking at in SRAM. And so we do that, and then we reach value loop, which is going to assign the register 20 with the value of the value in SRAM stored at the address stored in X. And then afterwards, it's going to increment it 1. And so we get that 27, which is our first value, and then we are going to get the value that is now in X now that we've gone up 1, and that is going to be 81. So we got 27 and 81 over here, and those are now stored in register 20 and 21. We're going to compare the two, and we're going to say, okay, if register 20 is less than register 21, we don't need to do anything, and we'll just skip to increment. And in this case, it is. And so we increment R19, which is the number of values that we've gone through, and then we compare R19 to R17, which is, again, the number of values that we've gone through versus the number of values that we are expecting to go through. And then, because they are not equal, we branch back to value loop and repeat the process. And now in the next case, we have 51 and 30, 51 and 30 in hexadecimal, which happen to be 81 and 48, respectively. And so each one is compared again, and because 81 is greater than 48, it's not less than, this will not skip to increment, and so X, the current location of X is where the 48 is, but the 81 is stored in R20, so we're actually going to store the value of R20 back in X, and then pre-decrement and store the value of R21, so we are essentially swapping them. And then because we have decremented X, we need to increment X again to stay on track with our values so that we can continue looping through each of the values. And so as you can see, these two have now swapped places because it was different. And so in this case, we're just going to repeat this process many times until we eventually get to a point where our 18, which is our number of times we've gone through the loop, is equal to the number of times that we expect to go through the loop, which is 19. And so it's a long process, but each time that you see a red on the right on memory 4 in the SRAM, that means that two values are being swapped. And as we can see, every time that they're swapped, it's because a value was greater than on the left of a different value. And so we're just going through the process of sorting each one of these. And now we have gone through all of those and gone through the increment every time, just as always. And then we reach this reset loop here. And so every time that the current number of values gone through is equal to the expected number of values that we should be going through every loop, we compare the current number of loops we've gone through to the current number, or the expected number of loops that we go through, which is that 19, because it's, again, in -1. And so if it's not equal, we keep returning, but because it is equal, then we eventually reach this return, which returns to the jump main statement, which jumps back to main. And this is because we have not, we do not have a current active subroutine. If there was a subroutine that was currently active, then we would actually jump to the original spot where that subroutine was called, but there is not one. So we go back all the way to jump, which is why when we go here, we get back to jump main. But as we can see on the right over here, all of our values that were in this table are now sorted and in SRAM. And so they are all in sequential order. And yeah, so that is it for this code segment.
For part 3 of our code, we're looking at this C code up here, which assigns 3 unsigned character global variables and computes an XOR computation on the C variable and subtracting the B variable from that. And the assembly equivalent code is shown here. So the way it functions in the assembly is it loads the global C variable into register 25, and then the 2 value to be compared to that in register 24. Then the exclusive OR operation is performed between R24 and R25, so 2 and 2, which results in just 0. And that value is stored in R24. And then the value from global B, which is 1, is stored in register 25. And so the value in register 25 is then subtracted from 24, so you get 0 minus 1, which results in 255 because they are unsigned characters. And then that value is now stored as global A. And I can show you this in real time. So we start out with R24 and R25 is 0. Then we load the data from global C as 2 in R25. Then 2 in R24, exclusive OR, changes R24 down here to 0. Then subtract the 2 values after loading R25 in as 1. And you get FF, which is just 11111111, which is also 255. And then stores that in A, and then returns from the subroutine.